Hey math kids, today we're going to go over some of these coordinate geometry problems. These are all similar to the ones on your homework, but they're not exactly the same. So the first one you'll encounter says we have a parallelogram and we're given the points C and B and we need to find point E. Now, property of parallelograms is that the diagonals bisect each other. So we know that these two segments, CE and EB, are congruent to each other. In other words, E is the midpoint of CB. We have a midpoint formula, and since we know the two endpoints, we can just plug it into that. Remember, it's just the average of the x's. So if we do 5 plus 1 divided by 2, and then the average of the y's, which is 2 plus 7 divided by 2, that's going to be 6 over 2. That's going to be, let's see, that was a 7. Okay, so that's going to be 9 over 2. And if we reduce that, it's going to be 3 comma 9 halves. And so that's the coordinates of E, and we're done with that. Now, another point, or another problem we'll come across, it's going to say something like, what is the equation of I forget how it's worded, but it's like, what is the equation for the set of all points exactly the square root of 2 from negative 1 comma 3? So that's really just asking, what is the equation of a circle? Now, if we're exactly square root of 2 away from something, that's just the radius of a circle. Let's change the color on that. So that's the radius, and then this is the center. So we have a circle equation right here that we're going to use. And so we're going to say x, we change the sign, so plus 1, quantity squared. And then we do y, change the sign, so it's negative. And then we're going to square this number because it's the radius squared. And so that's just going to be 2. And so that's the equation of a circle that meets all that criteria. Okay, moving on to this. So we have a circle with center 1 comma 2. So 1 comma 2. And then what we're going to do is we're basically going to draw a circle that has a radius that allows for this to be on it. And then we're going to test to see if this is on it. So the question asks something like, is it possible for both of these to be on the same circle? And so you kind of ignore the second one for a minute, and we just want to figure out what the radius would need to be. And we're going to come up with a circle equation for that. Or we could do this straight distance formula. Because if we just find the distance between 1, 2, and 4, 5, that will tell us a radius. And then if we do the distance between 1, 2, and negative 2, 3, if those are the same, then they can be on the same circle. If those distances are different, they can't be on the same circle. So what I'm going to do, I'm going to erase some of this stuff up here. So might as well erase this too. Okay. So we're going to do the distance formula between these 2 points. I'm going to call this my x1, y1, and this my x2, y2. So we have distance is equal to, so we do x2 minus x1, square that, and then we do y2 minus y1, and we square that. Simplify that, that's going to be 3 and 3. So that's going to be 9 plus 9. It's going to be 18, and that's the square root of 18. Alright, now we just need to test that. Now I'm going to keep this as my x1, y1, but now I'm going to look at this one, and this is my x2, y2. cross that out just so it doesn't confuse me. Do the distance formula again. This time we get -2 minus 1, and we get 3 minus 2. Okay, that's going to be -3 squared. It's going to be 1 squared. I think I'll just erase this diagram. I don't think I need that anymore. Okay, -3 squared is +9. 1 squared is 1. So that's the square root of 10. Because the square root of 10 is not the same thing as the square root of 18, these cannot be on the same circle, given that the circle is centered at 1, 2, because they would create two different radius lengths. Okay. All right, moving on. Okay, so the next problem, we're given 3 points that make a triangle. So if it helps, you can plot those points out. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4. 1, 2, 3. 1, 2, 3, 4, 5, 7. And 1, 2, 3, 4, 7. All right. To me, it looks like it's a right triangle, but we should justify it, not just by looking at it. So this first point was 4, 3. This next one is 5, 7. And let's see, 4, 7. Now the one on your homework might not be as obvious. This one we can basically, because we know this is a horizontal line and we know that this is a vertical, because this is a vertical line and this is a horizontal line, it's going to be a right angle right here. Now let's pretend like that wasn't happening. I'm going to go through and show you how to prove it definitively. What we're going to do is we're going to take the slope of any two lines that we think could be right angles, and make sure that they're opposite reciprocals. So what I'm going to do is find the slope of this blue side, and then I'm going to find the slope of this yellow side and compare their slopes. So to find the slope, we're going to use the y2 minus y1, x2 minus x1 formula that's over here. And I'm just going to call this x1, y1, and I'll call this x2, y2 for now. And so we look at our y2, so we're going to get 7 minus 3, and we're going to do 4 minus 4. And so we get 4 over 0. Okay. Now, what that means, if we ever get 0 on the bottom, that's undefined. That's an undefined slope. So that tells us that it's perfectly vertical. Now, I'm just going to leave it right here as 4 over 0. And then let's look at this one is horizontal. So I'll just leave this as my y2, and then I'll do this one as x1, y1, and forget about these ones. So if we have x1, x2, we're going to, we should start with our y's. So 7 minus 7 over 4 minus 5. And so we get a 0 over -1. Okay. Once again, that means our slope is 0, and then we have something over 0. So this is kind of a special case where we have vertical and horizontal. Now, what would be happening if it wasn't vertical and horizontal is that these should be opposite reciprocals if it's a right angle. Now, what I'm going to do, because I'm realizing this might not help you on your homework, unless it's purely vertical, purely horizontal, and then we know, yes, it's a right triangle. So this one is a right triangle. But I'm going to modify this just a little bit. I'm going to change this last, this point to 3, 3, just so we don't have that horizontal and vertical thing going on. So I'm going to move this point over here. And we're going to redo the problem. Okay, when we look at that, it looks like it could be a right triangle. I guess I should have erased this as well. And then I'm also going to change this one. I'm going to move it down 1. So I'm going to change it to 5, 6. Okay. Now it looks like this one might be a right angle when we do it that way. At least just based on my drawing. 1, 2, 3, 4, 5. Oh, I didn't bring that out enough, actually. It should look more like that. Okay. All right. So that basically, that changed the problem. This is 3, 3. And then this is 5, 6. Okay. And we don't know if it's yes yet. So we'll get rid of that. Okay. So let's get rid of this, and this, and this. This, and this, and this. Okay. We're going to go through the same process this time. So I'm going to call this x1, y1. So we have y2's right here. So I'm finding the slope. Actually, this one looks more right to me. So you want to test all the angles technically to verify whether it's a right angle. If you find a right angle, you can stop, but you really need to test all 3 if at all possible. And so we're going to find the slope of all 3 of the sides and then see if any of them are opposite reciprocals. So I'm going to find this line first, or this side first. And so we have 7 minus 3 over 4 minus 3. We reduce that. That's going to be 4 over 1. So the slope of this line is 4 of that side. Okay. Now, I'm going to change this to x2, y2. Forget about this one. So now we're finding this side. So now we get 5, no, that's the x value. We're going to do 6 minus 3, and then 5 minus 3. So that's 3 halves for this one. And now I'm going to call this x1, y1, so we can find this side. Okay, so y2 is 6, y1 is 7, x2 is 5, minus 4. So it's going to be negative 1 over positive 1, and so the slope of this is negative 1. Now, none of these are opposite reciprocals. So we know that these are both positive, so they can't be opposite reciprocals. So it would have to be like the negative 1 and the 4, or the negative 1 and the 3 halves. And so if we flip this upside down, though, so if we think of this like negative 1 over 1, we flip it upside down, that's going to be 1 over negative 1, and then we change the sign, so it's 1 over 1, which is just 1. So for something to be opposite reciprocal to this, it would have to be a 1 here or a 1 here. Because we don't have that, we don't have any right angles, and so the answer to this one is no. All right. Now this next problem, we're actually going to approach in the exact same way. I'm not even going to draw a diagram on this, but we're just going to find the slope between each of these lines, and if any of them are opposite reciprocals, or any that are corresponding. Actually, maybe we should draw it. I take it back. I'm going to draw it. 1, 2, 3. Let's see. 1, 2, 3. 1, 2, 3, 4. Okay, that should be enough. Negative 3, 0. 1, 2. 1, 2, 3. Negative 1. 0. Negative 1, 2. All right. It's kind of hard to tell if that's a rectangle. Definitely could be, at least from my drawing. Those could be right angles. Now, I should actually write these in. Negative 3, 0. 1, 2. 3, negative 1. 0, negative 4. So we're just going to test all those slopes. So I'm just going to say x2, y2, x1, y1. Okay, so we say negative 4 minus a negative 1, and then we say 0 minus 3, so that's like a plus sign, so that's negative 3 over negative 3, which is 1. The slope of that side is 1. I'm going to change this to x2, y2, forget about that one. So now we get 2 minus a negative 1, we get 1 minus 3, this is like a plus sign, that's 3 over this, let's see, that's negative 2, so the slope of this is negative 3 halves. Right away we know it's not a rectangle because this angle is not a right angle, because 1 is not the opposite reciprocal to negative 3 halves. Now, if it was a right angle, we'd have to test the other one. If that was a right angle, we'd have to test the other one, etc. And we could even try to do this with side lengths and things like that, but really the key is that it has the 4 right angles. Okay, if you need additional help, please come to Math Lab. Until then, calculator.